SwayamPrabha. Digital India. Educated India.
Welcome back. We are going to start a new topic, and it's on Exergy, and we'll examine the performance of engineering devices. Now, as we've already discussed this fact that the first law of thermodynamics is concerned with the quantity of the energy. On the other hand, the second law of thermodynamics is mainly deals with the degradation of energy during the process, or particularly concerned with the irreversibility or lost opportunity to work. So, in other words, if we describe a system and ask a question that what is the maximum amount of the work which we can extract out of the system, then we need to do certain analysis, and in order to do that, we'll define a term called exergy. So, our practical interest would be to find out the maximum work which we can extract from a given system having a certain specific state. Okay, as we know that heat cannot be completely converted to work, hence there is a certain limitation, and thus we would be able to analyze this limitation with the help of second law, in particular with the help of exergy or exergy balance. So, what is exergy? So, exergy is nothing but availability or availability of energy. It's nothing but useful work potential of a given amount of energy at a certain specified state. Okay. So, let us consider a system here. A system is nothing but a hot potato, and it's, let's say, at the boundary of the potato you have a 70 degrees Celsius temperature, and immediate surrounding there will be drop in the temperature until it reaches the temperature corresponding to that of its environment. So, at this condition the system reaches an equilibrium with the environment, and this particular state would be called a dead state. So, essentially, or the gradient of temperature is 0, and in particular it reaches an equilibrium. So, thus for a given equilibrium state, or if a system is at equilibrium with the surrounding, this would be defined as a dead state, and later you would realize that this dead state is indicative of the fact that this particular system has no specific value in terms of the work it can generate. We have already discussed this aspect earlier, that a system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of environment. And that is what we are going to reflect now, is that earlier we just discussed about the reversible process will deliver the maximum possible work, but now we are bringing this fact that the system undergoes transformation from the initial state to the state of its surrounding, that is the dead state. So, that change from certain pressure to T0 P0 essentially is the maximum possible, or this path would lead to the maximum possible work, and that is a system can deliver that. Okay. So, this particular would be a useful work potential during this process, and this would be calling as exergy. Okay. So, the exergy, in other words, represent the upper limit on the amount of the work a device can deliver without violating any thermodynamics law. Okay. So, we will discuss this aspect more in detail. So, let us first look at a specific example to understand the maximum possible work for a given system. So, this is about furnace which transfer heat at a temperature of 1100 Kelvin at a steady rate of 3000 kilojoules per second or kilowatt, and what we need to find out is the rate of exergy flow associated with this heat transfer. In other words, what is the maximum useful work which we can extract from this furnace, and we have assumed this environment temperature to be 25 degrees Celsius. So, we already talked about the fact that your maximum possible work is for the reversible process. In other words, we will be considering this furnace as a heat reservoir that supplies heat indefinitely at a constant temperature, and the temperature is 1100 Kelvin. Okay. So, we can model this particular system as a reversible heat engine and ask the question, what is its efficiency. So, this can be written as 1 minus T0 by Th. Okay. And this is going to be your maximum thermal efficiency. Okay. So, you can put down the values here 298 Kelvin divided by 110 Kelvin, and this turned out to be 72.9%. Okay, that means this particular reversible heat engine can convert 72.9% of heat in from this furnace to work. Okay, which essentially means that Exergy of this furnace is nothing but is equivalent to the power produced by this particular reversible heat engine. Okay, or Wx max is W dot reversible, which is going to be this efficiency of this reversible heat engine multiplied by Q, and this Q is already given to us as 3000 kilojoules per second. This turns out to be 2187 kilowatt. Okay. Okay. So this particular maximum work is basically the amount of work that a reversible heat engine operating between the furnace and the environment can produce. Okay. So in other words, the remaining 27.1% of Q is actually not available for doing any work. Okay. So this would become unavailable energy, which is nothing but total energy of the system, okay, of the system, let us say in this case furnace, whatever the energy being supplied here, minus of a system at the specified state, minus the exergy of that energy, okay, which essentially means that the amount of energy available is not 100%, and certain, for example, in this case, that out of 3000 kilojoules per second, only 72.9% is available for doing work, okay, and the rest of them are unavailable, and that is what this analysis demonstrate that exercise, and this is based on the reversible heat engine efficiency which we have used, okay, assuming the furnace becomes the source, or furnace was used as a reservoir to supply heat to the reversible heat engine. Okay. So let us continue and ask the question that what about the exergy of, let us say, kinetic energy or potential energy, which are the forms of mechanical energy. And as we know from our past exercises, that the kinetic energy and potential energy can be converted to work entirely, and thus exergy of kinetic energy is simply the kinetic energy, okay, and exergy of the potential energy is simply the potential energy. Okay. So however, this is not true if we consider internal energy and enthalpy, okay, which are macroscopic, molecular level microscopic energies, okay, and they are not entirely available to work. Okay. So internal energy and enthalpy are not entirely available to work. On the other hand, mechanical energy such as your kinetic energy, potential energy are entirely available to work, and thus exergy is directly related to the corresponding energies. Okay, and this is your schematic representation of total energy, and this only part which is available would be your exergy, the rest would be unavailable energy. Useful work. Okay, so let us look at the reversible work and irreversibility by using this piston cylinder device, and this is nothing but a closed system. Okay, so both are closed system, and if it is, as this particular system expands, it has to push the air, okay, which is outside the system, or this push the atmospheric air out of the way in order to push the piston outward, and thus it has to do certain work. Okay. So this work surrounding can be written as the atmospheric pressure multiplied by the change in the volume of the system. Thus the useful work would be the actual work minus whatever the work which the system has to do on the surrounding, okay, in order to change the system volume. So this is going to be W. This could be a loss or gain. For the case of gain, one can consider when the system undergoes compression, where the atmospheric pressure helps the compression process, and thus W surrounding represent a gain. Okay. For a constant volume system, okay, your useful work which we would write like a subscript u as simply as W. Okay, so that was the definition of useful work. Now we'll define reversible work now. So the reversible work is defined as the maximum amount of useful work that can be produced for the work producing device, or minimum work that needs to be supplied for the work consuming device as the system undergoes a process between the specified initial and final states. Okay. So that would be the definition of reversible work. So in other words, if the final state is dead, as we already talked about earlier, that Exergy, which we are going to define, is the maximum amount of work possible from a given state to the state where the system is at equilibrium with the surrounding, or which we say the dead state. So definitely the reversible work would be same as Exergy when the final state is the dead state. So that is what we emphasize here, that W reversible is Exergy in case final state is dead. Okay. And the difference between the W reversible and useful work is called irreversibility, because this is nothing but equivalent to Exergy which is destroyed, that means, or the work which cannot be used. Okay. That would be the corresponding Exergy destroyed. Okay. So we can consider this by using this particular diagram, that we have this initial state, okay, which follows a reversible process to undergo changes from initial state to final state. So using a reversible process, the work corresponding would be W reversible. In case of an actual process, the corresponding work is useful work, okay, and so the useful work would be less than the reversible work, because reversible work would be where there is no irreversibility, and hence is going to be more for work producing device. On the other hand, it is going to be opposite, that means less for work consuming devices. So here we are going to consider for work producing device where the maximum work is for the case of reversible work or reversible process, and hence your W reversible is greater than W useful. So the difference between them would be corresponding to the irreversibility. Okay, and this is nothing but equivalent to Exergy destroyed. Okay, so that's your I, which is the irreversibility, would be your reversible work. Now we will define out, which essentially means it corresponds to work producing device, minus the useful work which is out. Okay, so it's clear that if you want this performance of a system to be maximized, then I should be minimum, okay, or I should be minimized. Okay, for the case of a work consuming device, you can write this in opposite way, or you can write it in this following, or you can write as W in minus W reversible in. Okay, the reason why we have done this, because the W useful in is going to be more for work consuming device compared to the reversible. Okay, or as I said, the performance of the system can be improved by minimizing the irreversibility. So certainly when I goes to 0, when the irreversibility goes to 0, the work approaches towards that condition of reversible process. Okay, or useful work approaches to the condition of that reversible process. So let us try to analyze this further with an example. Okay, this is an example of heat engine receiving heat from a source of 1200 Kelvin at a rate of 500 kilojoules and rejects the waste heat to a medium at 300 Kelvin. Power output of the heat is 180 kilowatt. Determine the reversible power and the irreversibility rate for this process. Okay, so this is a schematic representation. So in order to find the reversible power, we simply have to make use of your thermal efficiency for the reversible heat engine, okay, multiplied by Q in. Now this is given in terms of your sink T source, okay, multiplied by Q in. T sink is 300, T source is 1200, Q in is 500. This turns out to be 375 kilowatt. So now this is basically nothing but the maximum power that can be produced by the heat engine. That is, this is the available power for the condition of sink at 300 Kelvin. So your I would be simply W reversible out minus W useful out. Okay. Now what is the reversible out? Of course, reversible out is this 375. What is useful out? That is what is for your system, and this gives you 195 kilowatt. So, this is of course not maximized, and this, because this is not maximized, because I is not minimized, I is the irreversibility, it turns out to be 195 kilowatt. So, there is a loss of 195 kilowatt due to irreversibility. Okay. Now, note that the input heat is 500 kilojoules per second, that is 500 kilowatt. Thus, your 500 minus 180 is 420. Out of 420 kilowatt, 195 kilowatt is due to irreversibility, and around 125 kilowatt is the heat which gets rejected to the sink. So, this is not available for conversion to work. Okay, so this was the example of making use of a reversible heat engine and demonstrating the irreversibility. Now, let us look at a little bit of analyzing the performance of or realistic performance of devices based on second law of thermodynamics. Now, thermal efficiency of COP based on first law does not address the realistic performance of the devices, and this we can understand based on a simple illustration. So, here for example, in this case you have two particular device A and B. Okay. Thermal efficiency both have 30%, however source are at different temperatures, assuming sink to be environment at the same temperature. Okay. So, based on your reversible heat engine efficiency, the maximum efficiency for A is 50%, for B is 70%. So, certainly it appears that the thermal efficiency of this is relatively performing much lower compared to its maximum ability. So, we need to come up with a better way to represent in order to show the thermal efficiency, okay, because this is certainly not giving us the indication of its performance, considering that they both have the same value, but it has a different corresponding maximum thermal efficiency. Okay. Thus, we need to come up with a better way to represent the performance of the devices. So, what we do is we look at the ratio of this, the thermal efficiency with respect to reversible heat engines, or the efficiency corresponding to reversible heat engine or corresponding to the maximum thermal efficiency, and that is what we come up with this particular second law of efficiency, which we define as eta 2. Okay, 2 stands for second law. The second law of efficiency is a measure of performance of a device related to its performance under reversible conditions. Okay. So, thus we simply take the ratio of the actual thermal efficiency to the maximum, that is the reversible thermal efficiency under the same condition. Okay. So, this is what I was referring to. So, we can simply take this as a ratio. Now, with this we can go back and look at again the same two particular devices, and clearly we can write eta 2A becomes 0.6 and eta 2B becomes 0.43. Clearly it indicates that the second device is performing inferior to your first device, which is A. Okay. The second law of efficiency can also be expressed in terms of your useful work. So, you can write this in terms of simply the amount of useful work for the particular device divided by the maximum possible amount which can be extracted from this device. So, this is the expression for work producing device such as turbine, piston, cylinder, and certainly it cannot exceed 100%. And similarly, you can also express this for your work consuming device, where we put R reversible in the numerator and useful work in the denominator, because of course this is going to be less than the W useful, and since we want the efficiency not to be more than 100%, and for the consistency we consider this definition for the work consuming device. Okay. Similarly, for your refrigerator we write this. Okay. So, this is for the refrigerator or heat pump. Okay. So, now this particular definition which we have made use of it clearly indicates that these are either for work producing device or work consuming device. However, what we want to do is make use of a definition which is generic in nature. That means it need not be just confined to the work producing device or work consuming device. Okay. Therefore, we need a more general definition, and what we are going to make use of general definition, it will be in terms of exergy or work potential. So, eta 2 would be exergy recovered, okay, divided by exergy spent, okay, or in other words we can write it in terms of 1 minus exergy destroyed divided by exergy expended. Now, we are going to spend more time on this definition and as well as making use of this efficiency in terms of exergy in the later part of this particular topic. Okay. So, here I will stop for this particular lecture. In the next lecture, we will discuss more of exergy destruction and particularly more about exergy. So here I will stop and we will discuss continue this exergy discussion in the next lecture. Okay, so see you in the next lecture.